Hello guys, this tutorial is the remake of my old one, Radial OPI menu. This has better approach both in quality and overall logic. I also decided to make two separate videos. The first one is procedural material and master widget, so you can manipulate particular sector. This approach is also based on the concept from Apex Legends game. And you can download the sample project. The link is under the video. So to start with, we need to create the material function which is called bisector. From the preview you can see that we have sort of mask. Here we can decide the sector count and sector rotation. So for instance, if we go for sector rotation like 0, you can see rotation is changed, and for sector count let's go with 4. You can see sector size is also changed. To have this one we need to have custom rotator first. So if you take a look at how it looks, you can see that we have the UV with the center in the middle of our plane. If you don't go with these manipulations, that's what we'll receive. So that's why we need to subtract 0.5 from our UV and make rotation center vector to 0, 0. Also, you can see that in this material function we have two inputs, function inputs, a sector rotation and sector count. The reason I have them separate is because we will change them via blueprint later. Overall logic is quite simple. 360 is the overall angle of our pi menu, of our circle. That's why we divide this by sector count to receive the bounds of our sector. But to make it look better, as you can see, we need to have divide our sector bounds by 2, so it's sort of the bisector is coming from the center of our angle, where the bounds are between, if we go with the 0 one, 35 and minus 45 degrees. Then we need to somehow change it to the dimensions between 0 and 1. That's why we divide overall logic from here, our value, by 360. Next one is vector to radial value, which help us to create the radial bisector. The first one, like my previous approach, was using only this part of logic, but if you take a look at how it looks, you can see sort of aliasing, and the mask that we have, the white one, is actually too sharp, and I don't like the result of it, so I created another one. And if you take a look how it looks now, you can see that the difference between black and white is has better transition. It's more smooth one. So if you go with something like, for instance, 4, you can see how the edges are blurred. So vector to radial value, we need to mask the R channel. It can be any channel, we just need to have this value converted to float. Then is if node, where we need to actually see in which parts of our coordinate we need to mask out our sector. For this, we use 360 divided by sector count to receive the bounds, and then we need to convert these bounds to dimensions between 0 and 1. So that's why we divide this one by 360. And then we check if A is higher than B, we go with white color. If it's not, we go with the black color. Then we need to invert our mask. So that's how it looks now, and that's how we need to look it after. Next one is radial coordinates here, and we need to have the following operations to make the smooth transition. We need to multiply sector count by the radial coordinates, then we use f mode by 1, and we use multiply the result of this one by 1 minus x, so we have sort of mirrored edges. So that's how it looks. And we need to use the clamp node. So as you can see, this one is has the same UV coordinates as our mask here. Yep, but we don't need to have all 4 parts of our UV. So that's why we need to clamp the result of this one with this mask. Sorry, we need to clamp this mask with the results of this one. And this will actually return smoothly, return the mask with smooth edges here. So next one is Pi menu, our master material. I decided to make it look like this so you can see the flow and overall logic better than before. So you can see that I have some components: green, blue, red one, and white one. Green one is the chosen color. It means that if I select an element and open up the Pi menu, you will see which element was the last one to be selected. Active color here is for like if you change the position of our mouse, you can see what element I'm going to select. Search color here is our small sector, which will which help us to see in which direction we are going to change our sector. And the fill color is like overall color of unselected items. Logic is quite simple. Here we need to multiply each color of each sector by particular mask. Then we add all these colors and go to the final color. So this part is for the color, this part is for the opacity, this one is to create sector mask, and this one to create sector. To create sector masks, we need to have few radial gradient exponential functions. As you can see, I have density and dimensions. It's vector 4, but we have, as you can see, separate channels for separate control, and the result of subtraction of each this mask will lead us to particular mask. So this one is our outer circle, which will go to the chosen color. This one is our active color, active mask. This one is for the search color, search mask. And then receiving this one, we need to multiply each particular mask by each particular bisector function to receive the following masks: this one, and this one. We also need to have the fill mask, the particular area which is not selected. So that's why we need to subtract particular masks and add results together to receive this one. So, sorry. How to receive this one? Density for each particular mask is to create smooth transitions between each sector. So we subtract from chosen one here the default radial exponential material function. The radius by default is 0.5, so that's the maximum. So that's why, let me see where I have it. That's why dimensions for each sector, for each mask, should start with 0 and end with 0.5. Next one is we subtract from the results of this mask this big one with the active one to receive smaller one, this one. And the last one is subtract from our active one, our search one, to receive the smaller one, this one particular. Next thing is to multiply each particular mask, as I said, with particular bisector function, this one. So we have sector count equally or the same for each bisector function, and chosen angle here are the same just for the preview sake. So they all share the same angle here. We will multiply chosen angle with the first one. Let me show you this one with the first one. Then the result of subtraction here with the second one is our active angle, and the search angle here with the result of the last one, this and this one. Then we need to subtract from the result of this mask the smaller one to receive inverted version of our search angle, and the same inverted version of our fill mask, of our active one. Then we need to add them together and receive this one. As I said, the results of each multiply goes and multiplied by particular color. So we have this one, this one, this one, and fill color with this mask. Next part is to use alpha channel of each particular color node to manipulate independently the opacity of each particular mask. So that's why chosen color alpha channel goes with multiply of the first one, then active color with this one, and so on. Then we need to add everything together and use it as the opacity for our overall material. So that's how it looks. That's how it works. Now let's talk about our widget. So we need to create simple widget blueprint and use image here. Alignment is 0.5, 0.5, so it's in the center of our viewport. Size, it depends on your purposes. And that's it. Next thing is to create the logic. So as you can see, that's the overall logic here, and nothing more we need at all. On the pre-construct, I use create dynamic material instance of my pie menu, then store it as the reference and use it as the brush for my image, for my pie menu, this element. So make sure it's set to be variable. Then here I decide the sector count, how much elements I need to have in this widget. So that's why you set scalar parameter on the py-menu material instance. And don't forget to to provide the proper name. So sector count here is the same name that we have for the sector count here. Next thing is to decide the sector size. So that's why I use 260 divided by sector count. So that's how I have sector size. Next part is to make the bounds for each particular sector. So if we have, for instance, 6 sectors, it means that sector size is 60. For each sector, bounds are different. So for the first one, it's 0, 60. Next one is 60, 120. The third one is 120, 180, and so on. The tricky part is to start loop with the 1, so the sector goes with the 1 first. So we have 6 sectors. The first one 1, and the second and the last one is 6. Next is we need to multiply index by the sector size. And if we add sector size like this, we'll receive the maximum bound. And from this, if we subtract sector size, we'll receive the minimum bound. But to make the smooth transition, so let me show you. Like this one, if my search angle is going to the bisectors and is higher than it, you can see how selection is done. So only on the mean and maximum values of each particular mean and maximum bounds. I hope you understand what I'm trying to say. So if you don't go with division by 2, we'll receive that sectors will be changed only on wrong conditions, only on the minimum, on the maximum, not this precisely middle one. And I have sector max bounds. It's the array of integers. The same is for the sector min bounds, also array of integers. So if we have 6 sectors, each sector has its own minimum and maximum values, bounds. That's it. That's the preparation for the creation of our widget. Next is event tick. Here we need to calculate the current rotation inside our viewport. For this we use mouse position from our own in player. We use only X and Y axis, and we get viewport size divided by 2 to make our center from the center of our screen. Then we use simple find look at rotation and use only that axis. From 180 we subtract this value and we receive current rotation. So if we print out the value, you'll see how it goes. Also, you can see that as the cut coordinates goes, our 0 always comes from the from this one, from the right part, middle right part of the coordinate system. Here is 90, here is 180, here's 270, and 360 goes to 0 again. So then we use current rotation as the search angle attribute for our material instance to change the direction of this red mask. In my case, if I have material instance, it's this one. the yellow one. And the last tricky part is to decide which sector we need to select to be used inside the active area, this one, the gray one. For this, I use for each loop with the break and iterate through the min bounds array. Then I check only for the validation purposes that array index inside my first array is the same as we have in second one, is our max bounds. If it's true, I can actually go and do the magic. Each array index here has its own bounds. I check whether my current rotation that I have on my viewport is inside the bounds of minimum and maximum values of particular sector. If it's so, I use array index plus 1 because I start with the 1 here, multiply by sector size. That's my current sector angle, my current sector. Then I break it so I can set scalar parameter active angle with current sector angle, and that's how this part will be selected. If and one more condition, if I'm out of the 360 dimension, because I'm trying to rotate, like I can have more than 260 degrees rotation, I simply use sector count, multiply by sector size, and use this as a current sector angle. So it starts with the 0 and to 360 again, and also break it. The last part is event construct. So once I'm selecting my element and then reopening my pie menu, I need to have my chosen item correctly highlighted. So that's why I use current sector angle and use it as the attribute for the chosen angle inside material instance. Now let's add everything inside the third-person character, and here is the logic. On event begin play, I simply create the widget, store it as the reference, but not add to the viewport. On R key here, I check whether my widget is actually valid. If it's so, I add it to viewport. If it's not, I remove it from parent. By using this one, widget is created and stored, but and every element here are not cleared. So we only just remove it from the viewport, but everything here is stored in the memory. Then I have simple boolean just to make it look better. If my pie menu is open or closed, and deciding on this value, I select the input mode for my game, whether it's game and UI or game mode only. And that's it, that's how it works. I hope you understand everything I was trying to explain you. So everything is under this video, my Patreon, my Discord, and yep, subscribe, leave your feedback, and see you soon.